back in my pocket. Uh, are there any questions so far? I know we're slowly moving through the actual development of this, but it's necessary to do it that way. We've done short dipoles, the actual small loop antennas, then multi-loop. Remember, I posted that for more than one turn up there, everybody. Then then we're about to do arbitrarily long wire antennas. And then I'm going to tell you where we're going. Once we do this and get the power and the directivity, then what we end up doing is array antennas. And after array, we go into things like the Friis transmission equation that deals with the actual how much signal you're going to recover with an antenna, not just transmit. And then we do radar. A radar is basically you transmit a signal, it strikes an object, and the reflected energy you have to pick up. And the time delay gives you the distance basically. And the actual signal strength coming back, you can infer the size of the object. So we're going to do this. Now this is going to be an arbitrarily long antenna. So now we're going to talk about, I'm going to just call it long dipoles. We have to do monopoles too, but you'll see dipoles, long dipoles. What do I mean by that? The length of the antenna is now of the order of a wavelength or more. So what we always do is start with a center fed antenna like such. We're going to assume it has a total length L, and it's fed at the center. Call this the z-axis. There's going to be a current distribution on this. Now, I don't test you on your knowledge of the current distribution and things, but in order to really appreciate this, you have to have an understanding of it. And keep in mind, what I'm trying to do is teach you as if you're going to be engineers, not technicians in the field. So I'm trying to give you insight into all the stuff that you would need to know to do antenna engineering or design. Here, the actual current density or current on the antenna, it would look like this. It always is at 0 at the end, and it would do something like this. Now this current profile, this is an I of Z. An I of Z is easiest to give. This is something, there is not a closed form solution for this. This is developed by consistent iterations, and I can only tell you that it's more complicated than it would seem to be to get this, because the way you solve this is solving Maxwell's equations with boundary conditions on a finite thickness antenna. And what you end up doing is getting really a solution that keeps on getting refined and better and better. What we've got here is an approximation, though, just telling you this. This is an approximation for the current on this. It'll have some magnitude, I naught. Then it's times the sine of beta. And then inside here, it'll be L over 2 minus the magnitude of Z. That's the current. This is assumed to be 0 here. And that's versus Z, so this would be L over 2, and this would be minus L over 2. Does everybody follow me? Z is in the vertical direction. Now, just so you can appreciate why this solution does work, or at least one reason. If you go ahead and make Z L over 2 at the top, right? I get L over 2 minus L over 2, or 0. The sine of 0 is 0. In fact, it meets that boundary condition. The current goes to 0 here. It also goes to 0 here, right? Because then if we have L over 2 minus the magnitude of minus L over 2, it's still L over 2 minus L over 2, or 0. And the sine of that's 0, right? Now here's the one caveat to this. When I'm right here, what is it? Well, there it's going to be sine of beta L over 2, right? And depending on what beta L is, remember beta is 2 pi over lambda. L, if it's lambda, then I got what? I mean, think about this. If beta is 2 pi over lambda, if L is lambda, I have 2 pi, right, over 2 pi, right? Or, excuse me, over 2. So I have pi. And the sine of pi is?
1.
Sine of pi over 2, 90 degrees, is 0. It means it would go to 0 here. Now, if it was a wavelength long, you would have this kind of current distribution, all right? You're feeding right here, you literally have no current going in. It means the impedance of that antenna is about infinite, just so you know it. You follow me on this? Now, you would like that, but there's a downside to that also, because the pattern you get isn't a preferred pattern usually. Just keep in mind, there's a lot of tricks to this. I'm just telling you some of the oddities when you start doing this. And there's some very smart people in here, and you see through this, you see, well, what about this, and what about this? And I'm trying to tell you, I know the current fed into this antenna, if it's 0, For any voltage, it sounds like nothing's being radiated, but in fact it is, because it never goes to an absolute zero. Keep in mind, this is an approximation, right, to a high degree of accuracy. It will feed current in there. It's the impedance is so high that you're going to get a huge amount of radiated power, because, you know, the impedance itself is a thing, I squared times the impedance. Well, you can have a very small amount of I, but a huge impedance, and you radiate a lot of power. All right? Something to think about. So now, how do we get the E field from this, or the H field? He does the H field. I like the E field. Here's what we're going to do. We're going to say, if I have a little, first I'm going to do one thing. I'm going to get rid of that current so I don't have a clogged board. That's the current. And here's the easiest way to do it. Come up here at a height Z. All right? Go ahead and take a chunk of current here. Well, that current is some I of Z, right? Y'all with me? It's got a thickness dz. So this looks like a little short dipole here. You can think of it that way. Can everybody appreciate that, class? Now, the way we do it, the way it's classically done, is you're going to take a radius vector r here, and you're going to say that r is much greater than the length of the antenna away. We're going to ensure we're in the far field. Now, next to this, and I'm going to say this point of observation out here where I'm getting the E field is a long way away. Now I take another ray, and this is about parallel to that one. Follow me? I'll call this R, I'll call this R prime. This is the one from the actual differential chunk of current right here going out to this point. Think about this. If I have something spaced this far away, where really he's the center of my antenna, here's where my chunk of current is that I'm talking about the differential actual electric field from. If I go from here to Haley Center, and I look at the difference in radius vectors, they're the same length, they're about parallel, follow me? The difference in length can be gotten this way. If I look at this, I can say this difference in length, if these are parallel rays, would just be equal to Z times cosine of theta. That would be the difference in length from R prime. This would be really R minus R prime. Can you all appreciate that, class? Because they're parallel rays, right? Come on. You can think about it this way, right? Long way away, parallel, right? This is R prime. This is R. Down here, this distance right here is just going to be the cosine of this angle times this distance Z. That's it. You can go ahead and mess with this later, but that's what the difference is if you assume they're about parallel. So now with that in mind, you can do this. It's important you do this. Just work with me on this one. Now I know the differential electric field for a short dipole. If I just put differential electric field, assume it's a short dipole, I know it's really J eta beta over 4 pi divided by distance r. Since r is about the same thing as r prime, I'll leave it as r. They're a long way away, got it? Now I take that, I know I'm going to have the sine of theta here, right? That's going to be involved. Then I have I of Z. Well, what's I of Z? It's I naught times the sine of beta times L over 2 minus the magnitude of Z. Everybody appreciate that? For a short dipole, this right here is really the I value, the magnitude, and I have to multiply it by dz to get the differential length in there, right? Everybody follow me? In case you're not following me, remember for a short dipole, in general, the E field is given as J eta beta over 4 pi r. This one you have to know. Then it's times e to the minus j beta r times the sine of theta a theta. And something I didn't put in here is the I naught times L. Well, we don't have an I naught that's a constant. We have an I of Z that's a variable. And I of Z is the thing that we're going to actually, that gives us the magnitude of I, and the thickness or the length of that is dz instead of L. Follow me? So that's how I'm modifying this over here. Eta beta 4 pi, that is my I naught L here. Follow me? I of Z times L. Then I have to get the phase, and here's the important part. Then I have e to the minus j beta right here. And instead of r, instead of putting r prime, now I put r minus z cosine of theta in here. The reason I did it, normally it would be just e to the minus j beta r, but my r is this r prime, and r prime would be equal to just r minus z cosine theta. Can you all appreciate that, class? Now I know this looks a little messy and too much going on, but we can break this down in a heartbeat. This is the differential electric field from that. Now notice one thing. The thing I'm going to be integrating over is dz to get the total electric field. Got it? Can you all see that? Everything that doesn't depend on dz I take out in front. So I end up with this. I can say that the E field is equal to, and I go ahead and I take out everything I can. So I have J, I have eta, I have beta over 4 pi r I naught. The sine of theta I can take out in front if I want. It gets absorbed back in here in a second. And then what I can do is integrate, or I can take out, if you look at this exponential, I can break this down to then e to the minus j beta r, take that outside. And then I can get that double integral from minus L over 2 to L over 2 of what remains of sine of beta times L over 2 minus the magnitude of z times e to the plus j beta z cosine of theta, and then it's dz. Now, something I'm going to say, this angle theta when you're a long way away, the difference in theta from the top of the antenna to the bottom is insignificant because we're so far away. It's like parallel rays. Follow me? Think about looking at a star and moving over a couple of feet. Your azimuth and elevation do not change. That's basically what we're saying. We're that far away. Now, I come down to this and how to do this integral. First thing you're going to say is, what about this sine theta? That gets absorbed into the answer. Follow me, class? That'll go away. Well, when you do this, I'll tell you how I do it. Now, the book, he doesn't do it this way. He looks it up in a table. You see this right here? We're not going to do the whole thing. I always do this. Anytime I have anything with a sine times an exponential, I know that sine of theta is equal to e to the j theta plus e to the minus j theta over 2j. Do you all agree with that? What's the name of that identity? It's one of three. Euler's, right? It's one of Euler's. Well, if I go in here, and for theta I put in beta times quantity L over 2 minus magnitude of z, I bust that up. Do you all agree? Then what are you going to do? You're going to collect all the exponential terms, and you'll notice this will be a function just of z here. It'll be a constant times z times another constant times z. You factor all that out, and you can go ahead and do integration on each one of the exponentials and get the final form. Do you all hear what I'm saying, class? Now you can do it I always suggest people to do this. If you're interested in this stuff, do it once by yourself, convince yourself, and you never have to do it again. You never have to reinvent the wheel over and over again. You just got to convince yourself it's right one time for the sake of your sanity. Then the final answer, the one that everybody uses, they get it in a very condensed form that's easy to understand. They say this whole 9 yards after everything is said and done. What this will come out to be is write this down, it's not Wentworth's book, J60 over R, right? Then it's going to have I naught, right here, the magnitude, e to the minus j beta r, right here. And then there's going to be this angular term that I want you to write down. Length doesn't enter into this. Then there's going to be a cosine here of beta, of beta times L over 2 times the cosine of theta minus cosine of just beta L over 2 divided by the sine of theta. Now, in your book, you're going to see something like this, and this is the E field. Remember, what I've got here, let me put this down as the E field. That is the E field, and it's in the A theta direction. I want you to take note of something. See this right here? That is how the thing varies with angle. Follow me? Everybody. Now, that right there is the E field, not the power pattern. All right? It's not the power pattern. When you do the power pattern, you could take 1/2 the real part of E times H conjugate. We'd have to get H, correct, class? Or the way I told you, if you're in free space, what did I tell you to do to get power density? 1/2 magnitude of the E field squared over eta, right? Or 1/2 eta times magnitude of the H field squared, right? Either one does it. And since this is free space, you can do it that way. But what that'll do is square this angle. Got it, everyone? So what Whitworth does, and hear me, Whitworth does this. When he goes through here and he gets the power density, P Av, as a function of angle and R, what he does, yes, we should technically say 1/2 the real part of E right there crossed H conjugated. But for our cases, because we're assuming free space, we get 1/2 magnitude of the E field squared over eta in the AR direction. And in his book, he's going to have this. Help me out here on the page number. He's going to have 15, and then it's going to be I squared. Actually, I got to be careful because I do this in a couple different classes, and sometimes he uses. Yeah, this is going to be 50. Yeah, it's 876 is the one, or 873, I guess. Either one of those. And it's I naught squared over pi. That's an I naught squared over pi, pi squared r squared. Now r is the radius vector. I think he uses a small r. I use a large r. And then he's going to have f theta here. All right. He's going to have f theta. Now, here's what f theta is. It's simply that function right there, that angular function squared. So he takes that function, cosine of beta L over 2 cosine of theta minus cosine of beta L over 2 divided by sine theta. And he simply takes it and squares it, and he calls that his f of theta. Now, in some of the other books, they will call this function some angular function like g of theta or f of theta, and then they'll just show a squared operator there, but they're the same essential thing. If you're looking on the internet, you're going to see a lot of stuff like that, because I know the internet's useful for giving you supplemental information and try to, especially if you're looking at things like Khan Academy, for some of the remedial stuff, he does a great job. But they're going to have different nomenclatures for this thing. Just remember that. There's different symbols. So that he's just taking this angle right here, this functional form and squaring it. And that's the power density right here, P Av. Now, what is important to understand is this function right here. If you take a look at this right here, before when we thought about the short dipole right here, if I got the power pattern, I'm basically squaring the E field, right? You all see how that sine squared would appear here, class, for the power density. All see that? So when you do the normalized power density for this one, it's just sine squared, right? Everybody see that? Here's the danger. This doesn't have a magnitude of 1, maximum magnitude. What you actually have to do is calculate what F max is for this one, and then divide it into this angle. So write this down. Now when you take a look at P normalized for an arbitrarily long antenna, you get rid of R, but still a function of theta. And what you have to do is take F of theta and you divide it by the maximum value of this. And that can be much greater than 1. It can be 4, 5, 6, 7. If it's a full wavelength dipole, it's got a maximum about 4 for that function. Understand? For just a half wavelength dipole, it'll have a maximum of 1. I'm going to do these examples, but I want you to appreciate the fact you can't just take this thing, that thing squared, and call it P normalized. It's not P normalized. You have to figure out the maximum value. By the way, how do you find out the maximum value of a function if you don't know what it is? This is a function of theta. Take the derivative with respect to the variable theta and set it equal to 0. Find out where that 0 is, correct, in terms of angle. Then you got to take that angle and go back into the function and evaluate it. Do I bore you to death that bad?
No,
Oh no.
test
Oh,
Friday and slowly getting into.
don't worry. Go back to bed. It's all right. Yeah, I know you know your stuff. It's just I'm feeling really bad. Like
No, I'm keeping up with my face down. I'm getting old.
this is going to be a good class. I mean, for the entire quarter or semester, it's going to be amazing. I can imagine. You all with me, class? I know this guy. He's sharp, so I'm not worried. Everybody all right with that? Now, why did I say I need P normalized there? What am I going with this, anyone? Very right. The directivity. I want the directivity because that is indicative of the gain once I find the antenna efficiency, right? It's going to be close to the gain. So what's the directivity? Well, in D max, let's do the maximum value. The maximum value for the directivity is 4 pi over what's called the solid angle, right? Please hear me on this one. The solid angle would be that integral of the normalized power density, P normalized, as a function of theta and phi, really just a function of theta in our case, has to take that times the sine of theta, then d theta d phi. Now phi will go from 0 to 2 pi almost always. Theta goes from 0 to pi for any kind of a half-wave dipole. For monopoles, it'll only go from 0 straight up to 90 degrees. Monopoles are above the Earth, and I'll cover that later. But this will give you the solid angle that goes here, and that's the maximum value directivity. And then we'd get the gain, if we needed it, by finding the antenna efficiency times the directivity. And that's the maximum gain. Do you all agree with that, class? The gain in general is the maximum gain times the normalized power pattern. I want to say that several times. So if I want gain in general, I always run out of board, but I'll put it here. In general, gain is a function of theta and phi is going to be the maximum gain times the normalized power density. And that's important. And that's used all the time. I'm going to tell you one other thing, that a lot of the stuff I'm saying here, I'm kind of underscoring, even though it seems simple and obvious, things that I know people make mistakes on. I know people make mistakes on this. Guaranteed. I see it every semester. I teach this course, and it's usually one of these things, somebody's half there in class, and they don't bother going through with care what this could mean. Because that thing, if you take it for a full wing, a dipole of full length, you're going to get a maximum value of about 4.5 to 5 for that angular function. Actually, it's squaring that, I think. So, wait a second. I better be careful. It's going to be greater than 1, less than 10.
Wouldn't that max out at 4 though if the first cosine term is, well, I guess sine doesn't have to be 1,000 or
I'm going to go through some of the examples. And by the way, there's a couple of weird things that happen with this thing when they get for large values of L. For now, just accept that, all right? All right, now that we have that, radiation resistance I'm going to mention too for this antenna. And these are things I got to tell you about. For an arbitrarily long antenna, let me go back here for a second. If you have an arbitrarily long antenna, there is no closed formula that you can use to get directivity. You see this integration right here? That is not something that has generally a closed form solution. It takes you have to use a computer to do a numerical integration. Everybody understand that? Now there are special cases that do have a closed form, and I'm going to do some of them for you. And they pop up all the time because this antenna is especially useful because it's got a fair amount of radiation resistance, and it's very easy to construct exactly. And there's no odd things where you're going to get some where all of a sudden you can get a type of resonance effect that'll cause your circuit to malfunction, like you're going to get an impedance that's going to go to infinity or something. It's a very stable type of circuit, and I'm about to show you that too. But I got to show you the radiation resistance. So for an arbitrarily long dipole, we'll go here. When I've taught this in the past, I'd go through these integrations, and I realized it was a magnificent waste of time because people would just, I don't know, go to their phones or tune me out until it was done. All right, let's do it this way. That I can get directivity, right? I can get if I could get the beam width. Do you all agree? If I plotted the patterns, I could figure out the beam width if I had the normalized power density. I just figure out where that value P normalized went to one half, right? And then I'd figure out the angular really distance from where it goes to one half to peak to one half again, right? So you could find out the beam width. Now, some of the other things you'd like to know is the total power radiated, and P radiated you can get by just taking, you can get this by taking a double integral of the power dense, of really, he likes to use the normalized power, but you can actually take the power radiated, and that's 15 over pi squared, I naught squared, and then it's times that f of theta, I'm not going to put that in there, times sine of theta, d theta, d phi, and you have to take this, the r squareds will cancel, so I don't need to show. Theta goes from 0 to pi, phi goes from 0 to 2 pi. One thing you're going to see is that if I did this right, I could divide that by F max and take F max outside, and then I could use the normalized, this power density, power radiated would be equal to that, and that would be equal to simply 1/2 I naught squared times R rad. So there's no I naught squareds would cancel. You could take twice that and get R rad if you wanted to. Do you follow me on this? In his book, he shows you a couple other things you can do to make life easy. He says if you want the total power radiated, you could just take R squared times the solid angle times the maximum power density at a given range R. And he shows you a few other tricks in 878, 879. I prefer you don't try to memorize these things. I prefer you do it this way. If I have this, really, this right here would be divided by R squared, and then your differential surface right here would have R squared. Because differential surface in spherical coordinates is going to be R squared sine theta d theta d phi. Do you all remember that? For constant R distance away. Now, I know that that R squared would cancel this R squared, so I don't normally put them in. I know that. The key thing is right here. This right here and f of theta, which is, remember, the squared value of the cosine of beta L over 2 cosine theta minus beta L over 2 minus cosine of beta L over 2 all over sine theta. Something I'm going to tell you, when you square that, you have a sine theta here, but you have a sine squared down here. You're still going to have a sine theta downstairs when you do the integration. And that almost always means go to the numerical stuff. And he has in MATLAB. Now, people have a thing, at least when they're starting with MATLAB, they hate it. MATLAB is used everywhere. MATLAB and Python are two things that are everywhere. If you go to Intel, if you go to Archangel over here, if you go to any of the national labs, any of the military places, I've been at Eglin Air Force Base, been at NASA Langley, been at NASA in Huntsville, I've been at Redstone Arsenal, working for the Army, working for the Navy, at Dogden at the Naval Surface Warfare Center. Everywhere, all the prototyping codes, when you're an engineer, a young engineer, they're going to ask you to write a code to do something. It might be something that's going to be for maybe a microcontroller, a microprocessor that's going to control something, right? You're going to write it in Python or C or MATLAB. One of them three, and you can't get away from it. If it's a microcontroller, it's C. If it's going to be for something else, a higher level thing, like a microprocessor, it's probably Python type of thing. Then if it's going to be something that's going to involve fairly complicated mathematics, you're going to use MATLAB, almost guaranteed. Some people will want it in, has anybody heard of Mathematica? All right, the reason people use Mathematica are primarily they're research scientists. It gives the output format. It'll do symbolic integration, differentiation, solve stuff. But the output is in a form called LaTeX. How many have heard the term LaTeX around here? If you're going to write journal papers and you're going to have a lot of complicated equations, you're going to write in LaTeX. I use LaTeX religiously. Word is okay, but Word has a big problem with formatting large equations and other things. Just hear me now. I'm trying to give you a heads up. If you had Marcus He's probably made you use LaTeX. If you're going to have some of the upper level courses from Mark Adams and stuff, they will ask you to use probably LaTeX and Mathematica hand in hand. Now, Mathematica, I'm just learning to use this myself. That is fantastic for getting the output into a form you can easily insert into a document. Remember that, because you're going to be doing this. A lot of you people have no idea the amount of writing you're in for when you become, first 5 years as an engineer in the field. If you're doing anything high-level technical, you're doing any design, you're writing and writing and writing. And one of the things that used to take so much of my time is creating equations for these things. You know what math type is, anybody? You know these WYSIWYG things where you're trying to get a long mathematical equation, right? And you put it in with Greek letters and all that. Well, you can spend hours doing this stuff on some of them. I'm not kidding. Things like Mathematica make that stuff go that fast. That's the reason. And I'm just telling you, somebody has to go through the pain of doing that. I hate that stuff, but just try. I'd like write it down, give it to somebody. Or you key it in. I don't want to do this, but you're going to get used to it. All right, now he gives the equation for radiation resistance and for power radiated for an arbitrarily long antenna. Now we get the special case of a dipole antenna that's half wave. This is very common all over the place, and I'll show you a couple tricks with half wave dipoles. Bless you. So now we're talking about a long antenna, but now the length of this antenna, L, is going to be lambda over 2. So this is the classic lambda over 2 dipole. There's a lot of reasons this is interesting. First, you know, for this, it's still going to have a symmetric current, right? It's going to have a current like this. If this is z direction, and this I of z here is the interesting thing. I of z, now if it's a half wavelength, it's I naught here. Then it's going to be equal times the sine of beta times L over 2 minus the magnitude of z over, well, that's the current there. Let me just put it down there. Beta is equal to 2 pi over lambda, and L is lambda over 2. That's all you have to know. So that means at 0, I have basically 2 pi over 2, or I have the sine of 90 degrees or 1 here. Follow me on this? So it means right here at 0, when z is 0, I have I naught is feeding my antenna. That means this current flowing in, this current flowing out. This is differentially driven, is I naught. That's the first thing you have to notice. So we're going to have a peak current fed to the antenna at that point. And it would be peak for anything shorter than that too, basically. For lambda over 2 on down to the shortest of the short dipoles, you're feeding at the peak current level. Are you with me? Now, that's important. Second thing that you realize is the antenna pattern. Remember, the E field in general is equal to J60 over R, R, times I naught, whatever that is, e to the minus j beta R, and then it's times cosine of beta L over 2, cosine of theta, minus cosine of beta L over 2, all over sine of theta, and the A theta direction. Now, here's the thing you got to notice about this. That's it for any arbitrarily length antenna, right? Specifically, we have a length of lambda over 2. It's a half wavelength. So when I look at this term, beta L over 2, beta is 2 pi over lambda. L is lambda over 2, and there's another 1/2, right? Are you with me what I'm doing here? Now, what do you see this becoming? Well, that 2 cancels that 2. The lambdas go away, right? And I have pi over 2, don't I? So that means here, for this thing, E will be given as J60 I naught over R, e to the minus j beta R, and then it's cosine of pi over 2 cosine of theta over the sine of theta. But notice what happens here. Beta L over 2 right there is going to be pi over 2, right? Or 90 degrees, correct, class? Well, what's the cosine of 90? Cosine of beta L over 2, class? 0. So we don't even need it. Probably another reason this antenna is so popular. That's the E field. Got to tell you one thing. See this function right here? That's the square root of f of theta, isn't it, in Whitmore's book? Because f of theta, he deals with the power. So now from that, we get f of theta, and that's equal to simply cosine of pi over 2 cosine of theta over the sine of theta. I'm about to tell you you're going to like. Technically squaring that, right? That's f of theta. Here's the nice thing about this one. The maximum value for that's 1, which is real nice. That means your normalized power density for this one is just that. So P normalized for the half-wave dipole is just equal to this. Cosine of pi over 2 cosine of theta over the sine of theta, squaring it, which is nice. Now I have the normalized power density. Now we can plot, by the way, from this right here, we can plot the pattern, can't we, class? Right? If we were to plot this, you're going to see it's almost the same as a short dipole, which is nice. Almost the same, but there's one super fact about this. Short dipoles have very low input impedance. This has a fairly high input impedance, which makes it preferred. So I have the normalized power density. When I have that, next thing I could do is get what? Directivity, right? And I could go ahead and say that, well, the D max at least for this would be equal to 4 pi over the beam solid angle. And the beam solid angle for this one would be a double integral from 0 to 2 pi. From 0 to pi of that, which is cosine of pi over 2 cosine of theta all over sine of theta squared times the sine of theta times d theta d phi. And you can do this integration. Let me give you a heads up. The d phi from 0 to 2 pi doesn't do a thing except bring out a 2 pi. You all see that, class? Now, when you're doing this integral in here, you see I got a 1 over sine squared times sine, so it's a 1 over sine, right? 1 over sine is cosecant, right? Then I have a cosecant times this stuff, and that's where all of a sudden the integration gets a little hairy. That's where you're going to do different types of tricks. You remember back in the day when you had all those trig integrals in calculus? You learned all sorts of different substitutions, correct? Well, I don't bother with that anymore because you guys have something called symbolic calculators. They do symbolic integration, and if there's a closed form available, it's available to you. I don't waste. I used to do these things. The way I do them is a little different, though, than the book. What I always do whenever I see a cosine like that, I turn it into, I use Euler's identity. E to the j theta plus e to the j, e to the minus, e to the j theta plus e to the minus j theta over 2. I would do that to the cosine. I do the same thing to the sine. All right, the sign that's left. Then you start manipulating. You get it down. You're going to get a single exponential, couple of single exponentials that you can't integrate. But I'm not going to even bother with that. Now, in your book, depending on which book you've had for calculus, they made you memorize all sorts of secant squared substitutions and all these other things. Remember? I don't care for that anymore. That's long gone. It's past me. I don't do it anymore. I don't expect you to. You've got symbolic calculators. I think, don't most of your calculators do symbolic integrations? Yeah.
Do you expect us to have a symbolic calculator
No.
for the test?
No, I don't ask you to do bizarre integrals.
Okay.
That's higher level stuff. And the advanced emag courses, then you basically have to use brute force and awkwardness to get the answer. And all sorts, you learn all sorts of specialty. You have to one time. That's the only way you can really appreciate stuff. But the majority of the stuff, you're just going to do it on your calculator or your computer. So this, the whole 9 yards of this, when it comes down and you do the integration, you're going to see that this thing right here comes out, and you can look at your book as 1.64. after all is said and done. That's what it comes down for D max. I want to tell you this, D max for a short dipole, this would be for a short dipole, is 1.5. You see how the directivity is not much better than the directivity of a short dipole? Everybody see that? As a matter of fact, if you looked at the patterns, and I'm going to try to draw these here, if we talked about an antenna, and the antenna was oriented in this direction, and it was a short dipole, for a short dipole you would have this. And you would basically have a beam width here of 100, or really, 90 degrees. Remember? It's from 45 to 135, or a beam width of 90 degrees. How many remember that for a short dipole? When you do R's, it's just a little bit better, just a little bit better. The beam width is going to be a little bit less, but not much less. And you can figure it out, but the way you have to figure out that beam width is you got to take this and set it equal to 1/2, and then solve for that angle. And there's two angles. It'll be symmetric. It's not much better. The beam width's very slightly better. Instead of being at like 45 degrees, it's like at 48.3 or something like that. I'm not kidding either. That's how slight a difference it is. But here's the thing where it's really nice. The radiation resistance of this for a short dipole, for a half-wave dipole, is the thing that really is good. And I'm going to put this down over here. The way you have to get this is numerically, by the way. I guess you could get it analytically, but it takes a little long because you need the total power radiated to get the radiation resistance. Here's what happens when you do this. This is for a λ/2 dipole. Please write this down. This is important. You're going to find out that the input impedance, Zin for the antenna, that's the input impedance to the antenna. It means if you have an exact λ/2, L would be λ/2, and this means exact, so I better put down the word exact. It has to be exactly that, λ/2 antenna. Then your input impedance right here, your Z antenna here, would be equal to 70, and he's going to, in his book, he's going to have 73.2 ohms plus J, and then it will be, let me see, that's 42.5 ohms is the one he has. Can you see in your book that impedance for a short dipole? 42.5. All right, he has that. Now here's the problem with what I'm telling you. The actual impedance of a short dipole is dependent on the radius. All right? If you get a very thin, super thin antenna, this will change slightly and this will change. You get something that gets very large, like now you're getting tenths of a wavelength in diameter, then what you're going to get is a bunch of reactance here. Follow me? So this is an approximation. It's not exact. It's about that. But what I'm about to tell you, it does work all the time. But if you can take that antenna, this is real important, and if you can trim it down, instead of being λ/2 or 0.5, if you take that antenna and you make it, or you shorten it to, now the length goes to 0.485 lambda, about, and I'll tell you how you do it. Then you get a Z antenna, Z input impedance, that is just this part, 73.2 ohms, plus J0. In other words, there's no reactance. That's preferred because reactance doesn't do anything to help us radiate. It's just more AC resistance to push against to get current into that thing. So we need a larger voltage. Got me, guys? This is real important. Now, how do you get it down to this? This is, by the way, it's not exact either. Here's how you can do it. When you're a grad student, you don't have billions of dollars worth of equipment, but you have nail cutters, nail clippers. I'm telling you, this is literally how they do it for some cases. You got wire antenna, you just paste it on a yardstick or something, or tape it there. You measure it, it's a half wavelength, right? You see that imaginary reactance. Take your nail clippers, off of both ends, maybe just like a millimeters off, right? You'll notice the input impedance falls down. Again, and you can see, you start snipping, pretty soon you get plus J0, you're done. And that's exactly how it's done in the real world a lot of times. The way they make these things is literally they just start snipping off the ends of these things because there's so much that causes that input impedance to change. Everybody thinks it's an ideal straight piece of wire, right? Well, let me tell you, long wires aren't straight. They wobble, they got bends that cause slight changes at the driving point. And the way you always do it is tweak. You always build in things that are basically system tweaks. You all know how to put a variable resistor, a pot in for something. If you need exact resistance, you'll put in the bulk of the resistance as a single resistor, and you'll put a potentiometer there that you can adjust to the exact resistance you need. Follow me? That's the way it's done in the real world with antennas too. You snip them off until you, when you're doing antenna design. Riggs knows a lot more about this than I do, by the way, because he worked for Harris and he did a lot. My antenna designs always boil down to the fact I had to do something for NASA. They usually, or the Air Force, and that usually involve fairly sophisticated, fairly expensive designs. First one had to be done right, and I learned my lesson never to use a technician to assemble and test. Always be there when they do it because somebody will not know something basic. And I mean, they could put a stick of chewing gum in there or something and foul the whole thing up. I didn't get to arrays. I'm going to do that Friday. On the test, we will not cover arrays on the exam, but everything up to this. All right? Test is Monday.
Will we have a quiz on Friday on any?
I'm not going to do a quiz Friday because test is Monday. Unless you want one.
There is an analog test.
Analog?
Yeah.
Wentworth?
Clark.
Jason Clark?
Yeah.